Hello there, and welcome back to the Science Sleepy Minds. Tonight, you're lying somewhere soft, maybe a bed, maybe a couch, maybe that one weird recliner you swore you'd replace 3 years ago, but never did because it knows the shape of your spine too well. Above you, a ceiling fan spins lazily, its blades cutting through the air in that hypnotic rhythm that makes your eyelids heavy. You're watching it turn round and round, and you're thinking absolutely nothing important. Just breathing, just existing, just letting the day drain out of your muscles like water from a wrung sponge. But here's something your sleepy brain probably isn't considering. Time itself is doing strange things around you right now. Not metaphorically, not poetically, literally. The clock on your nightstand and the clock on a satellite 20,000 kilometers above your head are ticking at slightly different speeds. Your feet, dangling closer to Earth's center than your head, are aging a tiny fraction slower than your brain. You probably won't survive long enough to notice the difference, nobody does, but the difference is real, measurable, and frankly a little rude when you think about it. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment telling me where you're listening from and what time it is there. Someone in Tokyo might be waking up while someone in Buenos Aires is finally surrendering to sleep. And isn't that a strange thought? The same moment, experienced so differently. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You settle deeper into your pillow, and the ceiling fan continues its lazy rotation. Each blade passes through the same point in space, over and over, a circle repeated endlessly. It feels eternal in that sleepy, detached way things feel when you're not fully present. But that fan is lying to you. Or rather, it's telling you a story so simplified that it borders on fiction. Because time, actual time, the thing that separates your birth from your death, the thing that makes before different from after, is far stranger than any spinning blade could suggest. For most of human history, people assumed time was obvious. It flows, it moves forward. A second is a second is a second. Whether you're a pharaoh watching the Nile flood or a tired person in the 21st century watching a ceiling fan. This assumption felt so natural that nobody seriously questioned it for thousands of years. Sundials worked, hourglasses worked, church bells rang at the appointed hours, and everyone agreed on when lunch was. Time seemed universal, democratic, identical for everyone. Historians still argue whether ancient civilizations had any concept of time as a thing that could vary or stretch. Some scholars point to certain mystical texts, suggesting that gods experienced time differently than mortals. A day for a deity might be 1,000 years for a human. But these were religious metaphors, not physics. Nobody was doing math about it. Nobody was suggesting that a person walking down the street was aging at a measurably different rate than a person standing still. And yet that's exactly what's happening right now, to you. Here's a quirky tidbit that might keep you awake for exactly 3 more seconds before you dismiss it and sink further into relaxation. Every time you climb a staircase, you age slightly faster than someone who stayed on the ground floor. Not much. We're talking nanoseconds over a lifetime, but the effect is real, confirmed by atomic clocks, and completely ignored by everyone who's ever complained about having to take the stairs. You're not just getting exercise, you're fast-forwarding through your own existence, one step at a time. The ceiling fan doesn't care about any of this. It just keeps spinning, oblivious to the fact that its outer edges are moving faster than its center, experiencing time in a microscopically different way. If that fan could think, and thank goodness it can't because sentient ceiling fans would be terrifying, it might wonder why its tips feel slightly younger than its hub. The answer involves a patent clerk, a beam of light, and the complete demolition of common sense. But we'll get there. For now, just breathe. Feel the air moving across your face, stirred by those slowly rotating blades. That air is made of molecules bouncing around at various speeds, each one experiencing its own tiny version of time, though the differences are so small they'd make a gnat's heartbeat look like a geological epoch. You're surrounded by clocks, essentially. Trillions of tiny clocks, all ticking at slightly different rates, all averaging out into the smooth, seamless experience you call the present. The present? What a concept! You think of it as now, this single moment where you exist, sandwiched between the past you remember and the future you're gently drifting toward. But even that simple idea will get complicated before this night is over. Because now for you is not now for someone moving very fast relative to you. Your now and their now might disagree about which events have already happened and which haven't yet occurred. It sounds like nonsense. It sounds like something a philosophy student says at 2 a.m. when they've had too much coffee and not enough sleep. But it's physics. Verified, tested, confirmed physics. So close your eyes if they're not already closed. Let the fan's rhythm lull you deeper. We're going to take a journey through time itself, not by building a machine or finding a wormhole, but by understanding what time actually is. And the first step is meeting the man who gave humanity its first, rigorous, mathematical, gloriously wrong theory of how the universe works. His name was Isaac Newton, and for about 300 years everyone thought he'd figured everything out. You're drifting now, and somewhere in the back of your mind you can almost see him. A man with long hair, a serious expression, and absolutely no sense of humour about apples. Isaac Newton was born on Christmas Day in 1642, or possibly January 4th, 1643, depending on which calendar you trust, because even calendars couldn't agree on time back then, and from the moment he started thinking, the universe never stood a chance. Newton's gift to humanity was a clockwork cosmos. He looked at the chaos of existence, planets wandering through the sky, cannonballs arcing through the air, moons orbiting their parent worlds, and he found the hidden order beneath it all. His laws of motion were elegant, universal, and devastatingly effective. Push something, and it moves. The bigger the push, the faster it goes. Every action creates an equal and opposite reaction. Simple rules, profound consequences. But the real magic was his theory of gravity. Newton realized that the same force pulling an apple toward the ground was also pulling the moon toward Earth, and Earth toward the sun, and the sun toward the center of the galaxy. Gravity was everywhere, reaching across the void of space, tugging on everything with mass. He wrote down equations that could predict where the planets would be centuries in the future. Astronomers used his math to discover new worlds they'd never seen, simply by noticing wobbles in the orbits of worlds they had. The universe, it seemed, was a magnificent machine, and Newton had found the instruction manual. And time was the backdrop against which this machine operated. Newton called it absolute time, and he described it as flowing uniformly, without relation to anything external. Imagine a cosmic clock, ticking away somewhere outside the universe, marking identical seconds for everyone and everything. Whether you were on Earth or Mars, whether you were moving or standing still, whether you were a king or a peasant, that cosmic clock ticked the same for you. Time was democracy perfected. Everyone got the same amount of it per second, no exceptions, no special treatment. This idea felt so obviously true that it barely needed defending. Of course, time flows at the same rate everywhere. How could it not? A second is defined by being a second. The circularity didn't bother anyone because the conclusion matched everyday experience. You could synchronize two clocks, separate them, bring them back together, and they'd still agree. Time was reliable. Time was fair. Time was Newton's silent partner in the great mechanical dance of the cosmos. Historians still argue whether Newton himself fully believed in absolute time or whether he considered it a useful approximation. Some of his private writings suggest he was troubled by deeper questions. How could something flow if there was nothing for it to flow relative to? What did it mean for time to exist outside the universe, untouched by anything within it? But publicly, Newton presented absolute time as foundational, and the scientific community accepted it gratefully. Here's a quirky detail that might amuse your drowsy mind. Newton was famously petty about rival scientists. When Gottfried Wilhelm Leibniz independently developed calculus around the same time Newton did, the two men spent decades attacking each other's character, accusing each other of plagiarism, and generally behaving like toddlers fighting over a particularly shiny toy. Newton even used his position as president of the Royal Society to stack a committee investigating the dispute with his own allies. The committee ruled in Newton's favour, shocking absolutely no one except possibly Leibniz, who died shortly after, possibly of spite. Time flows uniformly for everyone, but Newton's grudges were eternal. You shift slightly in your bed, feeling the sheets adjust around you. The ceiling fan keeps turning, and somewhere in your mind you can picture Newton's universe operating like a vast pocket watch. Gears turning, springs unwinding, every component moving according to precise mathematical laws. The future was, in principle, entirely predictable. If you knew the position and velocity of every particle in the universe at one moment, you could calculate where they'd all be at any future moment. Fate was just physics, and physics was just math, and math was just complicated but manageable. This vision was intoxicating. It suggested that the universe was knowable, that chaos was an illusion, that underneath the apparent randomness of existence lay crystalline order. Scientists spent the next 2 centuries refining Newton's laws, applying them to new domains and marvelling at their accuracy. They predicted eclipses. They calculated the paths of comets. They built bridges and engines and machines that transformed human civilization, all using Newton's clockwork rules. And time kept ticking, the same everywhere, the silent metronome counting out the universe's operation. But there were hints that something was wrong. Small hints, easily ignored. When scientists studied electricity and magnetism in the 19th century, they found equations that seemed to predict a fixed speed for electromagnetic waves. That speed was suspiciously close to the measured speed of light, which suggested light itself was an electromagnetic phenomenon. Beautiful. Elegant. Except the equations didn't say the speed of light relative to what. They just gave a number, as if that speed were absolute, the same for everyone regardless of how they were moving. This created a problem. In Newton's universe, speeds were always relative. If you're on a train moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing beside the track sees the ball moving at 80 miles per hour. Speeds add up, that's just common sense. But if light's speed is fixed and absolute, it doesn't add up with anything. Whether you're moving toward a light beam or away from it, you should measure the same speed. That's not common sense, that's very, very strange. For decades, physicists tried to solve this puzzle without abandoning Newton. They invented a mysterious substance called the luminiferous ether, supposedly filling all of space, providing the reference frame against which light speed was measured. Clever experiments tried to detect Earth's motion through this ether. They all failed. The ether, if it existed, was being remarkably elusive. And then, in 1905, a young man in Switzerland decided to stop trying to save Newton and started asking what would happen if light's stubbornness were a fundamental feature of reality rather than a problem to be solved. The city of Bern in 1905 was a postcard. Cobblestone streets, medieval clock towers, the Our River curving through the old town like a protective arm. Trams rattled past cafes where serious-looking men discussed philosophy over coffee, so strong it could wake the dead. And in a modest building on Speichergasse, a third-class patent examiner sat at a desk covered in paperwork, bored out of his mind and quietly changing the universe. Albert Einstein was 26 years old, with dark curly hair and a moustache that hadn't yet achieved its future legendary wildness. He'd failed to get an academic job after university, possibly because his professors found him arrogant, possibly because the universe has a cruel sense of humour, and had settled for evaluating patent applications. Electromagnetic devices mostly. He'd review whether some inventor's proposed machine was novel enough to deserve legal protection, write a brief report and move on to the next one. It was, by most measures, mind-numbing work, but Einstein's mind refused to be numbed. While his hands shuffled papers, his thoughts wandered to deeper questions. He'd been obsessed with light since adolescence. Ever since he'd wondered what would happen if you chased a beam of light and caught up to it. What would you see? A frozen wave hanging in space? An oscillation that had stopped oscillating? The image troubled him because it felt impossible, yet Newton's physics seemed to allow it. If speeds are relative, you could theoretically match light's speed and observe it at rest. But Maxwell's equations, the mathematical laws governing electricity and magnetism, said light speed was constant. Not constant relative to some medium, not constant relative to some observer, just constant. Period. The equations didn't care how fast you were moving. Light would still pass you at exactly 299,792 kilometers per second. It was as if light were the universe's cosmic speed limit, and no matter how fast you drove, the limit stayed the same distance ahead. Einstein decided to take this seriously. What if Maxwell was right, and the speed of light really was the same for everyone? What would that mean for everything else? The answer came to him in pieces, assembled during walks and tram rides and sleepless nights that would have been much improved by a ceiling fan. He realized that if light speed is constant, then something else has to give. If you measure the same speed for light, whether you're moving or stationary, then the things you use to measure speed, distances and durations, must themselves be flexible. Time must flow differently for observers in relative motion. Space must contract. The sacred absoluteness of Newton's clockwork universe must be an illusion, a comfortable approximation that works fine for everyday speeds, but falls apart when you approach light's velocity. In June 1905, Einstein published a paper with the unassuming title, On the Electrodynamics of Moving Bodies. It contained no experiments, no references to other scientists' work, no apologies for demolishing 300 years of physics. Just thought experiments and mathematics, arranged with the cold precision of someone who knows they're right and doesn't particularly care whether anyone else agrees yet. Historians still argue whether Einstein was influenced by earlier thinkers who had circled around similar ideas. The Dutch physicist Hendrik Lorentz had already derived transformation equations that described how measurements of space and time would differ between observers. The French mathematician Henri Poincaré had speculated about the relativity of simultaneity, but neither had taken the final step. Neither had declared that time itself was relative, that there was no absolute cosmic clock, that Newton's beautiful certainty was fundamentally wrong. Einstein did, and he did it while stamping patent applications for electrical toasters. Here's a quirky detail that humanizes the moment. Einstein later admitted he was terrified no one would understand the paper. Not because it was complicated, the mathematics was actually fairly straightforward by physics standards, but because the conclusions violated intuition so violently. He worried that readers would dismiss him as a crank, some patent clerk who'd lost touch with reality while drowning in bureaucracy. He sent the paper to the Annalen der Physik, one of the most prestigious physics journals in the world, and waited. The paper was accepted. Physicists read it. Some were baffled. Some were intrigued. A few, including Max Planck, whose own work on energy quanta would later help birth quantum mechanics, recognized immediately that something profound had happened. The universe had just gotten weirder, and a young man in Switzerland was responsible. You let out a slow breath, feeling your chest rise and fall. The ceiling fan continues its rotation, indifferent to relativity. At the speeds that fan operates, Newtonian physics works perfectly well. Time dilation, length contraction, these effects are real, but they're so tiny at everyday velocities that you'd need impossibly precise instruments to detect them. The fan's blades age at almost exactly the same rate as its hub. Your feet age at almost exactly the same rate as your head. The differences exist, but they hide in the decimal places smuggled into the universe's fine print. Einstein's genius was recognizing that the fine print mattered, not because we'd ever notice it in daily life, but because the fine print revealed what the universe was actually doing. The comfortable approximations we call common sense are like a map that works fine for navigating your neighborhood, but falls apart if you try to cross a continent. Newton's map was excellent for cannonballs and planets and falling apples. But light was crossing continents, and the map was failing. In that cluttered patent office surrounded by drawings of inventions that mostly didn't work, Einstein had found a better map. It would take years for the physics community to fully appreciate what he'd done. It would take decades for experimental technology to catch up and verify his predictions. But by 1905, the revolution had already begun, and time, absolute, universal, democratic time, was its first casualty. You're sinking deeper now, the story carrying you along like a gentle current. Somewhere above you, the ceiling fan marks seconds that aren't quite the same as the seconds marked by your heartbeat. The differences are tiny, unmeasurable by any clock you own. But they're there, whispering Einstein's truth in a language of nanoseconds. Imagine you're standing on a train platform waiting. The night air is cool and a single lamp casts a yellow pool of light onto the concrete. In the distance, you see a train approaching, its headlight cutting through the darkness. That headlight is broadcasting photons, tiny packets of electromagnetic energy, and those photons are racing toward you at almost 300,000 kilometers per second. Now imagine you step onto a train moving in the opposite direction, speeding away from that approaching light. In Newton's universe, you'd expect the light to catch up to you more slowly. After all, you're running away from it. If the light is moving at 300,000 kilometers per second, and you're moving at 100 kilometers per second in the opposite direction, surely the light should only appear to be approaching at 299,900 kilometers per second relative to you. But that's not what happens. When scientists measure the speed of that incoming light, they get exactly the same number regardless of how fast they're moving. Standing still or sprinting away, the light passes you at precisely 299,792 kilometers per second. Not 1 meter per second, more or less. The light simply refuses to play by Newton's rules of addition. This is the stubbornness that shattered physics. For a while, you can almost feel the frustration of 19th century scientists trying to explain this behavior. They were so close to understanding. They knew light was an electromagnetic wave, which was a triumph of theoretical physics. They knew its speed, which was a triumph of experimental physics. But waves need a medium to travel through, right? Sound waves need air. Ocean waves need water. What did light waves need? The answer they invented was the luminiferous ether, a hypothetical substance filling all of space, invisible, intangible, and perfectly suited to carrying light from stars to eyes. The ether would provide the reference frame against which light speed was measured. Problem solved. except when scientists tried to detect Earth's motion through this ether, they found nothing. The most famous attempt by Albert Michelson and Edward Morley in 1887 used an incredibly sensitive device called an interferometer to compare the speed of light in different directions. If Earth were moving through a stationary ether, light should travel slightly faster in some directions than others. But Michelson and Morley found no difference. The ether, if it existed, was undetectable. Historians still argue whether Einstein knew about the Michelson-Morley experiment when he developed special relativity. He later claimed it hadn't influenced him much, that his reasoning came from theoretical considerations about Maxwell's equations rather than experimental results. But whether he knew or not, his solution was radical. There is no ether. Light doesn't need a medium, and its speed isn't measured relative to anything. It simply is, a constant of nature as fundamental as the charge on an electron or the strength of gravity. Here's a quirky thought experiment that might help this sink in. Imagine you're holding a flashlight on a spaceship travelling at 90% the speed of light. You turn on the flashlight, aiming it forward. Common sense says the light should now be travelling at 190% the speed of light. You're 90% plus the light's 100%. But common sense is wrong. The light travels at exactly the speed of light, 100%, not one photon faster. You can't add your velocity to it. The universe's speed limit is absolute. So what gives? If you're moving and light's moving but the speeds don't add up the way Newton said they should, something in the calculation must be changing. Einstein realised that the somethings were space and time themselves. Think about what speed actually is. It's distance divided by time, kilometres per hour, metres per second. If you travel 100 kilometres in 1 hour, your speed is 100 kilometres per hour. Simple. But what if your ruler starts shrinking? What if your clock starts slowing down? Suddenly the distance you measure and the time you measure become different from what someone else measures. And the speed you calculate from those measurements can stay the same even when the underlying motion seems different. This is exactly what happens at high velocities. As you move faster relative to someone else, your measuring tools, not just physical rulers and clocks, but space and time themselves, begin to distort. Lengths contract in the direction of motion. Time intervals dilate, stretching out, so that fewer seconds pass on your clock compared to a stationary observer's clock. These distortions conspire in precisely the way needed to keep light speed constant for everyone. It sounds like a cosmic cheat. It sounds like the universe is fudging the numbers to preserve some arbitrary rule about light. But it's not arbitrary. The constancy of light speed is woven into the deepest equations of physics, into the structure of space-time itself. It's not a rule the universe follows. It's a feature of what the universe is. You let your eyes rest, feeling the gentle pressure of your pillow against your skull. Above you, the ceiling fan continues its steady rotation, blissfully unaware that its blades are compressing by an unmeasurably tiny amount in the direction of their motion. At household speeds, these relativistic effects are so small, they might as well not exist. But they do exist. They're always there, lurking in the physics, waiting to become significant when something moves fast enough. And light moves fast enough. Light is always fast enough. It races across the cosmos at its universal speed limit, carrying information from distant stars, bouncing off your bedroom walls, entering your eyes even now if any light source is on. Every photon that reaches you has travelled at exactly the same speed, regardless of where it came from or how the source was moving. The universe, it turns out, is built around light's stubbornness, not the other way around. Newton thought space and time were fixed, and speeds could vary without limit. Einstein realised that speed, specifically light speed, is fixed, and space and time must vary to accommodate it. This inversion changed everything, and the first consequence, the one that captures imaginations and inspires science fiction, and makes physics students question their sanity is what happens when you have a twin. You have a twin. An identical one, let's say, born from the same fertilized egg, sharing your DNA, your face, your tendency to overthink things at 2 a.m. You grew up together, graduated together, and on the day you both turned 30, you stood side by side looking exactly alike. 2 copies of the same person. Then your twin got an offer, a journey to a distant star, aboard a spacecraft capable of travelling at 90% the speed of light. The trip would take 10 years each way by ship time, 10 years out, turn around 10 years back. 20 years of their life spent hurtling through the void, exploring a new solar system, gathering data that would revolutionize astronomy. You stayed home, you watched the launch from Mission Control, waved at the departing ship and went back to your life. You got a job, maybe 2. You fell in and out of love. You developed a few grey hairs and a deeper appreciation for comfortable shoes. 20 years passed on Earth, then 20 more, then a few beyond that, and then the ship returned. You're standing at the landing site now, older, wrinkled 60-something years behind you. The ship settles onto the tarmac, hissing and steaming after its long journey. The hatch opens, your twin emerges. They're 40, not metaphorically, not because of some skincare routine practice during the voyage. Physically, biologically, cellularly 40 years old. They've experienced 20 years since departure. Their heart has beaten 20 years worth of beats. Their hair has grown 20 years worth of length, then been cut, then grown again. For them, only 2 decades have passed. For you, over 40 years have gone by. You've lived more than twice as much life as your twin since the day they left. This is not science fiction. This is physics. This is what Einstein's equations predict with mathematical certainty, and what countless experiments have confirmed with increasing precision over the past century. The phenomenon is called time dilation, and it's one of the most counterintuitive results in all of science. When something moves at high velocity relative to you, time literally slows down for it. Not metaphorically, not perceptually, fundamentally. A clock on that spaceship would tick fewer times during the journey than an identical clock left on Earth. A candle would burn more slowly. A heartbeat would take longer between contractions. Everything that uses time as an ingredient would experience less of it. Historians still argue about whether Einstein fully grasped the philosophical implications of his discovery, or whether he viewed it primarily as a mathematical result. His 1905 paper presented time dilation as a straightforward consequence of the relativity postulates, derived with algebraic precision but little fanfare. It took other scientists and eventually the public to realize how deeply strange this was. Here's a quirky detail that might help this feel real. In 1971, physicists Joseph Hafele and Richard Keating put atomic clocks on commercial airline flights. They flew the clocks around the world twice, once eastward, once westward, then compared them to clocks that had stayed on the ground. The flying clocks disagreed with the stationary ones by a few hundred nanoseconds, exactly matching the predictions of relativity when you account for both speed and altitude effects. Time dilation isn't something that happens only at exotic speeds near light. It's happening on every airplane flight, every train ride, every time you jog instead of walk. The differences are just really, really small, but they're not zero. And at your twin speed, 90% of light, they're enormous. You look at your twin standing there in their 40-year-old body and you try to process what's happened. They haven't cheated death. They've just taken a different route through time. Both of you started at the same moment and arrived at the same moment, but your twin took a shortcut. The shortcut cost them 20 years of experiences you had, the jobs, the relationships, the grey hairs, but it also spared them 20 years of aging. Which of you has lived more? That's not a physics question anymore, that's philosophy. You settle deeper into your pillow, the twin paradox lingering in your mind like a strange dream. The ceiling fan above you is moving technically, but at such a slow speed that its time dilation is undetectable by any instrument humans have built. If the fan could think, it would age at the same rate as you. Its blades would wear out at the same rate as your cells. You're synchronized, you and that fan, partners in the slow crawl through time that defines life on Earth. But somewhere out there, in the vast universe you'll never visit, there are things moving fast enough that time bends around them like water around a stone. Particles in accelerators approach light speed and live longer than they should before decaying. Cosmic rays strike the atmosphere and create short-lived particles that somehow survive long enough to reach ground-based detectors. The universe is full of little time travelers extending their brief existences through the physics that Einstein uncovered. And you, lying here, are travelling through time too. 1 second per second, give or take. It's the slow way, the normal way, the way every human has ever done it. But it's still time travel. You're moving through the fourth dimension as surely as you move through the other three, even if you're perfectly still in space. Your twin understood this. That's why they left. Not just to see a distant star, but to experience what it feels like to take the fast route through time. Was it worth it? They saw things you never will, but they missed things you take for granted. Time is not fair, it never was. Einstein just showed us the math. Your spaceship, let's give you one now since you're clearly the adventurous twin in this scenario, is accelerating. The engines hum with a deep vibration that passes through the hull, through your seat, through your bones. Stars outside the viewport shift from white to blue as you pick up speed. They're like compressed by your motion. You're going fast, really fast. Not fast enough to notice the cabin shrinking, but fast enough that your clocks are starting to misbehave. On your wrist, you're wearing a watch. It's ticking normally as far as you can tell. Second after second, minute after minute, the hands sweep around the dial in their familiar rhythm. You check your pulse and find nothing unusual. 60 beats per minute, maybe 70 when you think too hard about the void outside. Your favourite song plays through the ship's speakers, and it sounds exactly the right length. Everything feels normal, but back on Earth things are different. Your friends at Mission Control are watching a live feed of your ship's instruments. They see your watch, displayed on a monitor, and they notice something strange. The seconds on your watch are taking longer than the seconds on their wall clock. When a minute passes for them, only 50 seconds seem to pass on your display. Your heartbeat, measured by the ship's biosensors and transmitted home, appears sluggish. Your song stretches out, its tempo dragging as if the playback was slowed. They're not malfunctioning, the instruments are fine. Time itself is flowing at different rates in different reference frames, and you're experiencing it firsthand. This is time dilation not as a thought experiment, but as a lived reality. From your perspective, nothing has changed. You're still you, still experiencing 1 second per second, still living at the normal speed of life. But relative to Earth, you've become a slow-motion version of yourself. Your clock is behind. Your life is lagging. Every second you experience corresponds to more than a second back home. Physicists have a formula for this, the Lorentz factor, named after Hendrik Lorentz, who derived the equations before Einstein gave them physical meaning. It tells you how much time slows down based on your velocity relative to another observer. At 10% of light speed, the effect is barely noticeable. Your clock runs about 0.5% slow. At 50% of light speed, the slowdown becomes significant. Your clock runs about 15% slow. At 90% of light speed, your clock is running at less than half its normal rate. And as you approach light speed itself, the slowdown approaches infinity. At exactly light speed, which you can never reach if you have mass, time would stop entirely. Historians still argue whether Lorentz fully understood the implications of his own equations. He derived them to explain the Michelson-Morley experiment's null result, showing mathematically how lengths and times must transform between moving reference frames. But he interpreted them as physical effects caused by motion through the ether, not as fundamental features of space-time. Einstein took the same equations and gave them a radically different meaning. There is no ether, and time dilation is real, not just apparent. Here's a quirky consequence that might tickle your sleepy brain. If you could somehow travel at exactly the speed of light, which you can't, but hypothetically, time would not pass for you at all. You would experience departure and arrival as the same instant, regardless of the distance travelled. A photon leaving a distant galaxy travels for billions of years from our perspective, but experiences no time whatsoever from its own. Light doesn't age, light doesn't experience duration. Light exists in an eternal now that spans the entire universe. You shift in your pilot's seat, watching the stars drift past. The ship's clock still looks normal to you, tick, tick, tick. But you know intellectually that those ticks are stretched out relative to home. Your streaming playlist, which you loaded before departure, will last longer for Earth-based listeners than for you. By the time you return, you might have heard it once, while your friends have heard it 1.5 times. This affects everything. Your thoughts, which are electrochemical processes in your brain, slow down relative to Earth. Your digestion, which breaks food into nutrients through chemical reactions, slows down. Your cells' division, your hair's growth, your nails' lengthening. All of it happens at a reduced rate as far as Earth is concerned. You're not in suspended animation. You're not frozen. You're just leisurely, taking your time, living at a pace the universe allows because you're moving so fast. The weird part, one of many weird parts, is that nothing feels different. Your subjective experience remains unchanged. You think at normal speed. You talk at normal speed. If you had a companion on the ship, your conversations would flow normally. Time dilation doesn't slow down your experience. It slows down your experience relative to someone else. This distinction matters. You're not being cheated out of life. You're living normally but accumulating less time on the cosmic ledger. Your heartbeat thuds steadily in your chest, and you realize that somewhere, far behind you now, Earth is spinning slightly faster than it seems. Morning and evening are cycling through your friends' lives more quickly than through yours. They're having more meals, more conversations, more moments while you drift through the dark. The gap widens with every passing second. And the ceiling fan in your bedroom, if it's still there, if your lease is still valid, if the building hasn't been torn down while you're gone, continues its lazy rotation, marking time in a reference frame that's slipping away from yours like two boats drifting apart on a dark ocean. Something else is happening to your spaceship, something you might not notice until you try to stretch your legs. The cabin feels the same size. Your couch is still 3 meters long, your storage locker still fits the same number of boxes, your personal space still extends from wall to wall as it always did. But if someone back on Earth could somehow photograph your ship as it streaked past, they'd see something impossible. Your ship would appear compressed, squashed, shortened in the direction of travel as if a giant hand had gripped the front and back and pushed them together. That 3-meter couch would measure 2 meters, maybe less depending on your speed. The storage locker would look like a briefcase. The entire vessel would seem flattened into a fraction of its normal length. This is length contraction, and it's time dilation's spatial sibling. Just as time stretches when you move fast, space contracts. Distances in the direction of motion shrink, compressed by the same Lorentz factor that slows your clocks. At 90% of light speed, your ship would appear less than half its rest length to a stationary observer. At 99%, it would be a sliver, at light speed itself. Impossible. But humour me, it would have no length at all. a two-dimensional pancake streaking through the cosmos. But here's the strange symmetry that makes relativity so elegant and so maddening. You don't notice any of this. Inside your ship, your rulers haven't changed. You measure the couch, and it's 3 meters. You measure the storage locker, and it fits the same boxes. You haven't shrunk, your instruments haven't shrunk, nothing has shrunk from your perspective. Length contraction, like time dilation, is a relative phenomenon. It describes how you appear to others, not how you appear to yourself. And this part tends to break people's brains. From your perspective, it's the universe outside that's contracted. Earth, speeding away behind you at 90% of light speed relative to your rest frame, appears compressed. The distance to your destination star has shrunk. What was supposed to be a 10 light-year journey now measures less than 5 light-years. The universe itself has accordion squeezed in the direction of your travel. Historians still argue whether Einstein anticipated the conceptual difficulties these ideas would create for students and the public. His mathematical presentation was clear, but the implications took decades to fully absorb even among physicists. Length contraction seemed to contradict everyday experience so thoroughly that many early readers assumed it must be an optical illusion or a measurement artifact rather than a genuine physical effect. Here's a quirky detail that might help ground this abstraction. Particle accelerators rely on length contraction to function. When protons are accelerated to near-light speeds in machines like the Large Hadron Collider, their circular path appears contracted to them. From the proton's perspective, the 27-kilometer ring is much shorter than it appears to us. This affects the timing of the experiments, the collision dynamics, the energy measurements, everything. Engineers designing these machines must account for relativistic effects, or nothing would work. You stretch out on your spacecraft couch, feeling its familiar 3 meters beneath your body, and you consider what this means. The universe isn't changing size, your ship isn't physically compressing. But measurement itself, the act of determining how long something is, depends on who's doing the measuring and how fast they're moving. There's no true length any more than there's a true time. There are only lengths and times relative to specific observers in specific states of motion. This is deeply disorienting if you think about it too hard. Our intuition insists that objects have definite sizes. A table is a meter long, period. That's its length. It doesn't change just because someone walks past it quickly. But at the speeds we encounter in daily life, the changes are so small they're undetectable. We live in the Newtonian approximation, where things have fixed sizes and time flows uniformly, and the weird truths of relativity hide in the decimal places. Your spaceship, though, is moving fast enough for the decimal places to matter. If you could see outside clearly, you'd notice the stars ahead appearing bunched together, their light blue shifted by your approach, their apparent positions clustered toward your direction of travel. The stars behind would spread out, their light red shifted, their positions drifting apart. The universe itself would look different because you're moving through it differently. This phenomenon has a name: stellar aberration. It's been observed since the 18th century, when astronomers noticed that stars' apparent positions shifted slightly, depending on Earth's motion around the Sun. At earthly speeds, the effect is tiny, a few arc-seconds at most. At near-light speeds, it becomes dramatic. The entire night sky would compress into a bright point ahead of you, with darkness swallowing everything behind. You're not travelling quite that fast, so your viewport still shows stars scattered across the black, but they're tinted, shifted, compressed. The cosmos is speaking a different visual language because you're moving through it at relativistic speeds. Your eyes, your brain, your entire perceptual system evolved to interpret a stationary universe, and now you're seeing what happens when motion becomes extreme. The ceiling fan in your memory continues its rotation, its blades maintaining their comfortable length. It will never experience length contraction worth measuring. It will spin and spin until it breaks, or until you replace it, and throughout its entire existence, it will remain properly three-dimensional, properly sized, properly Newtonian. Lucky fan, it never has to think about any of this. There's a thought experiment that tends to haunt people once they really understand relativity. It involves a train, a platform, and 2 lightning strikes. Einstein loved thought experiments. He called them Gedanken experiments, and this one in particular reveals something deeply unsettling about the nature of time. Imagine you're standing on a train platform exactly in the middle, with markers stretching out in both directions. A train passes by at high speed. At the exact moment the midpoint of the train aligns with where you're standing, 2 bolts of lightning strike simultaneously. One hits the front of the platform, one hits the back. You see both flashes at the same instant because the light from each travels equal distances to reach your eyes. The strikes were simultaneous. That's your observation, and you're certain of it. But there's someone standing at the midpoint of the train, and they observe something different. From their perspective, the train is stationary and the platform is moving. When the lightning strikes, they're moving toward the front flash and away from the back flash. The light from the front reaches them slightly before the light from the back. They don't see the strikes at the same time, and because they know they were at the midpoint when the strikes occurred, they conclude that the front strike happened first. Who's right? Both of you. And that's the problem. Simultaneity, the idea that 2 events happen at the same time, is not absolute. It depends on your state of motion. Events that are simultaneous for one observer can occur at different times for another observer, and there's no cosmic referee to declare whose version is correct. Both observations are equally valid, equally real, equally physical. This shatters something fundamental about how we think of time. We imagine a universal now, a single moment that slices through the universe, separating the past from the future. Everything that exists now exists together in the present, but relativity says there's no such slice. Now for you is different from now for someone moving relative to you. The present is local, not global. Historians still argue whether Einstein fully appreciated how philosophically radical this was. His papers focused on the mathematical and physical consequences, deriving transformation equations and making predictions. But the deeper implications, that the past and future might exist just as fully as the present, that the passage of time might be an illusion of consciousness, these questions would occupy philosophers for generations. Here's a quirky consequence that might keep you awake for a moment. If simultaneity is relative, then there are events happening right now on distant stars that haven't happened yet, according to someone moving differently than you. The order of events can depend on who's observing. For events separated by large distances, your present might be someone else's past or future. The universe isn't a stage where things happen in sequence. It's a 4-dimensional block where all of space-time exists together, and now is just a slice you happen to be experiencing. You feel your breath slow, your body heavy against the mattress. The ceiling fan rotates above you, and you wonder, what is now for the fan? What events across the universe are simultaneous with this moment, this exact instant of blades passing through air? The question doesn't have a unique answer. It depends on frame of reference. If the fan could think, its now would differ from yours ever so slightly because it's moving and you're not. Or you're moving and it's not, since motion is relative and there's no absolute standard. This is why physicists talk about space-time rather than space and time as separate things. Einstein, with the mathematical help of his former teacher Hermann Minkowski, showed that space and time are woven together into a single 4-dimensional fabric. Events don't just have locations in space, they have locations in space-time, with coordinates that specify where and when. And just as different observers can disagree about spatial distances due to length contraction, they can disagree about temporal intervals. The separation between events is a combination of spatial and temporal distance mixed together in ways that depend on your motion. Minkowski gave a famous lecture in 1908 where he declared that space by itself and time by itself are doomed to fade into mere shadows, and only a union of the two will preserve independent reality. It was dramatic, perhaps overly so, but the point stands. You can't fully describe the universe by talking about space alone or time alone. You need space-time, the four-dimensional structure that relativistic physics reveals. You try to picture it, a block of existence extending in 3 spatial dimensions and 1 temporal dimension, containing every event that ever has happened or ever will happen. Your birth is in there somewhere, a point in the block. Your death is in there too, another point. The distance between them is your life, a world line threaded through space-time, connecting moment to moment. Are all those moments equally real? Is your childhood still happening somewhere in the block? Is your future already there, waiting for your consciousness to catch up? These questions slide from physics into philosophy, and physicists tend to shrug and return to their equations. The math works. The predictions match experiments. What the math means about the nature of existence, that's someone else's problem. But lying here in this moment you're calling now, you can feel the strangeness pressing against your thoughts. The ceiling fan keeps spinning. Time keeps passing. But what is passing exactly? And is it really going anywhere? Somewhere in the universe, right now, a paperclip is sitting on a desk. It's a small paperclip, maybe 3 grams of bent steel, the kind you'd use to hold together a few sheets of paper. It costs almost nothing. It does almost nothing. If you lost it, you wouldn't bother looking for it. But that paperclip contains enough energy to level a city. This is the most famous equation in physics, the one that appears on t-shirts and coffee mugs, the one that even people who've never studied science can recite. E equals mc squared. Energy equals mass times the speed of light squared. Einstein published it in 1905, the same year he revolutionized our understanding of space and time, as a brief follow-up paper that almost seemed like an afterthought. It was only 3 pages long. It changed the world. The equation says that mass and energy are interchangeable. They're not just related, they're the same thing, measured in different units. The c² part is a conversion factor, translating between kilograms and joules, the way a currency exchange translates between dollars and euros. And because c, the speed of light, is such a large number, and its square is enormous, a little bit of mass corresponds to a staggering amount of energy. That 3-gram paperclip? Multiply 3 grams by the speed of light squared, that's about 90 quadrillion joules. The atomic bomb that destroyed Hiroshima released about 63 trillion joules. Your paperclip, if you could convert all its mass to energy, would produce more than 1,000 times that much destruction in a paperclip. This is why nuclear weapons are so terrifying and nuclear power is so potent. They don't create energy from nothing. They convert tiny amounts of mass into enormous amounts of energy. In a nuclear reactor, heavy atoms like uranium split apart, and the fragments weigh slightly less than the original atom. That missing mass becomes energy, heat, electricity that powers cities. In a nuclear bomb, the same process happens explosively, converting mass to devastation in microseconds. Historians still argue whether Einstein foresaw the military implications of his equation. He was a pacifist for most of his life, deeply opposed to war and violence. When he wrote E equals mc squared in 1905, he was thinking about theoretical physics, not weapons. But decades later, as World War II loomed and scientists warned that Nazi Germany might be developing atomic technology, Einstein signed a letter to President Roosevelt urging American research into nuclear fission. He later called it the greatest mistake of his life. Here's a quirky detail that might spark a sleepy thought. You're converting mass to energy right now, inside your body. The metabolic processes that keep you alive involve chemical reactions, where the products weigh slightly less than the reactants. The difference is released as energy, the heat that keeps you warm, the electrical signals that carry your thoughts, the mechanical motion that drives your heartbeat. It's an incredibly inefficient conversion. Chemical reactions tap only a tiny fraction of the mass energy equivalents, but it's happening. You are, in a sense, a very slow nuclear reactor, burning mass to sustain life. You breathe slowly, feeling your chest rise and fall, and you consider the implications. Every object in the universe contains latent energy locked in its mass. The walls of your room, the air in your lungs, the ceiling fan above you, all of it is stored energy, waiting for the right conditions to be released. The universe is a vast reservoir of potential destruction, masquerading as ordinary matter, but also potential creation. The same equation that enables bombs enables stars. The sun shines because it converts mass to energy in its core, fusing hydrogen into helium and releasing the difference as light and heat. Every second, the sun loses about 4 million tons of mass to this process, radiating it outward as the energy that warms your planet and powers nearly all life on Earth. You exist because mass can become energy. The atoms in your body were forged in ancient stars that exploded, converting mass to energy in the most spectacular way the universe allows. E equals mc squared connects relativity to the everyday world in ways that still astonish. It explains why accelerating a massive object to light speed is impossible. As an object speeds up, its kinetic energy increases, and that energy adds to its effective mass, making it harder to accelerate further. To reach light speed, you'd need infinite energy, which doesn't exist. Only massless particles like photons can travel at light speed because they have no mass to convert. This is why your spaceship from earlier can never quite reach the speed of light no matter how long you accelerate. You can get close, 90%, 99%, 99.9%, but that final fraction remains forever out of reach. The closer you get, the more energy it takes to go faster, until the energy required becomes larger than anything the universe can provide. The paperclip on that imaginary desk remains motionless, holding its city-leveling energy in quiet reserve. It will probably never release it. It will rust eventually and crumble, and the atoms will scatter into the environment, their mass energy still locked away. But the potential is there, always there, hidden in the silent equation that connects matter to energy, rest to motion, existence to the speed of light squared. The ceiling fan too contains enough latent energy to cause unimaginable destruction, but you're not worried. You know the difference between potential and actual. You trust the physics to keep mass and energy separate most of the time for most things. Sweet dreams, little paperclip, your power is safe for now. You're in an elevator, one of those fancy ones with smooth acceleration, the kind where you barely feel the motion starting. The doors have closed, the floor has begun to rise, and you're standing in a small metal box ascending through a building whose height you haven't bothered to ask about. Now imagine the cable snaps. This is not a pleasant thought, so let me soften it. The building is very short, there's a cushion at the bottom, and you'll be fine. But in the brief moment of free fall, before the safety mechanisms kick in, something magical happens. You float. Your feet lift from the floor. Your arms drift upward. The coins in your pocket rise gently toward your face. Everything in the elevator, you, the coins, the elevator itself, is falling at exactly the same rate. So there's no relative motion between you. You can't feel gravity. For this brief, terrifying, wonderful instant, you're weightless. This is the same weightlessness astronauts experience in orbit. The International Space Station isn't floating because there's no gravity in space. There's plenty of gravity, about 90% of what you feel on Earth's surface. It's floating because it's in free fall. The station is constantly falling toward Earth, but it's also moving sideways so fast that it keeps missing, curving around the planet in an endless plummet that never reaches the ground. Einstein had a profound realization about this. In 1907, 2 years after special relativity, he was sitting in his office at the Patent Bureau, still the Patent Bureau, still the bureaucracy, when a thought struck him. A person in free fall doesn't feel their own weight. They can't tell from local experiments whether they're falling in a gravitational field or floating in empty space far from any massive object. The two situations feel identical. He later called this the happiest thought of his life, not because he was morbid, but because he recognized something deep. Gravity and acceleration are intimately connected. They produce the same physical effects, and if they produce the same effects, maybe they're fundamentally the same thing. Historians still argue whether Einstein's happiest thought story is apocryphal or accurately remembered. He told the story decades later, and memory is notoriously unreliable. But the insight itself is documented in his papers from 1907 onward, a slowly developing idea that would eventually become general relativity. Here's a quirky thought experiment that might help this sink in. Imagine you're in a rocket ship with no windows, accelerating through empty space at exactly 9.8 meters per second squared. The same rate objects accelerate when falling near Earth's surface. Inside the ship, you'd feel weight. You could stand on the floor, drop an apple and watch it fall, pour water from a glass. You'd feel exactly as if you were standing still on Earth. Now imagine the rocket stops accelerating and just drifts. Suddenly you're weightless again, floating, reaching for handholds, no gravity. The feeling is identical to being far from any planet, far from any massive object drifting in the void. The point is this: you can't tell the difference. From inside the ship with no external reference, gravitational acceleration and rocket acceleration feel the same. This is called the equivalence principle, and it became the foundation of Einstein's general theory of relativity. You feel your body heavy against the mattress, pulled downward by Earth's gravity. But from a certain perspective, you could equally say that the Earth is accelerating upward toward you, pushing the mattress against your back. The two descriptions are equivalent. They produce the same physical sensations, the same mathematical predictions, the same lived experience. This sounds like a semantic trick like wordplay rather than physics, but Einstein saw deeper. If gravity and acceleration are equivalent, then gravity isn't a force in the usual sense. It doesn't pull objects the way a magnet pulls iron. Instead, gravity is geometry. Massive objects warp the fabric of space-time around them, and other objects follow the natural curves of that warped space. You're not being pulled down, you're following the straightest possible path through curved space-time, and that path happens to lead toward Earth's center. The mattress is accelerating upward, resisting the natural geometry, pushing against the curve, and you feel that resistance is weight. This reinterpretation changes everything. Newton said gravity was a force acting at a distance, one mass pulling on another across empty space with no mechanism. Einstein said gravity was the shape of space-time itself, determined by the distribution of mass and energy, telling objects how to move. The falling elevator, the orbiting station, the accelerating rocket, they're all exploring the same deep truth. Gravity is local, it's felt through acceleration and free fall, and it's inseparable from the structure of space and time. You breathe slowly, feeling the mattress support your weight. Somewhere far above, the ceiling fan traces its circle through air, that's itself held to Earth by the same warped geometry. Everything you've ever experienced, standing, sitting, falling, rising, has been a navigation through curved space-time. You just didn't know it. Einstein knew. It took him 8 more years to work out the mathematics, to find equations that described how mass curves space-time and how space-time tells mass to move. But the seed was planted in that patent office, in that falling elevator daydream, in the happiest thought of his life. The happiest thought led somewhere. It had to. Einstein wasn't the kind of person to leave an insight unexplored, to plant a seed and walk away without tending the garden. From 1907 onward, he wrestled with the implications of the equivalence principle, trying to extend special relativity to include gravity, to build a complete theory of how the universe works. It was hard, really hard. Special relativity dealt with observers in uniform motion. No acceleration, no gravity, just smooth gliding through space-time. Adding acceleration meant adding curvature, and adding curvature meant learning entirely new mathematics. Einstein spent years chasing dead ends, publishing partial results, collaborating with mathematicians who could fill the gaps in his geometric knowledge. The breakthrough came in 1915, after a decade of effort, exhaustion, and occasional despair. Einstein presented his field equations of general relativity to the Prussian Academy of Sciences, and when he saw that the math correctly predicted anomalies in Mercury's orbit that Newtonian gravity couldn't explain, he was so excited that he reportedly suffered heart palpitations. The universe had confirmed his theory before anyone had even finished reading it. The equivalence principle, gravity equals acceleration, was the seed. General relativity was the tree, and what a tree it became. The core idea is this: mass and energy tell space-time how to curve, and curved space-time tells mass and energy how to move. It's a beautiful feedback loop, matter shaping geometry and geometry guiding matter. The equations that describe this relationship are elegant in their symmetry, but brutal in their complexity. Only a handful of exact solutions have ever been found. Most problems require approximations and computer simulations, but the conceptual picture is almost Zen-like in its simplicity. Imagine you're an ant walking across a surface. If the surface is flat, you walk in straight lines. If the surface is curved, a sphere say, or a saddle, your straight line bends without you noticing, because you're following the surface's geometry. You think you're walking straight, but an observer from above sees you curving. Now extend this to 4 dimensions. Space-time is a surface, not a 2-dimensional surface, but a 4-dimensional fabric with 3 spatial dimensions and 1 temporal dimension woven together. Mass and energy create dents and curves in this fabric, and objects moving through space-time follow the fabric's contours, tracing paths that appear curved when viewed from afar but feel perfectly straight to the objects themselves. This is why planets orbit stars, not because gravity is pulling them, but because the star's mass has curved space-time around it, and the planet is following the straightest possible path through that curved region. The path happens to be an ellipse. The planet wants to go straight in a sense, but straight in curved space-time loops around and around. Historians still argue whether Einstein's general relativity was the inevitable next step in physics, or whether it required his unique genius to conceive. Other scientists were circling around similar ideas. The mathematician David Hilbert nearly beat Einstein to the finish line. But Einstein's physical intuition, his ability to connect abstract mathematics to observable phenomena, was unmatched. Here's a quirky detail that might amuse your drowsy mind. Einstein hated the term relativity for his theory. He preferred invariance theory, because the whole point was to find things that stay the same regardless of your frame of reference. The speed of light, the laws of physics, the space-time interval between events, these are invariant, constant, universal. but the name relativity stuck, probably because it sounds more dramatic and Einstein eventually stopped fighting it. You let your thoughts drift, imagining space-time as a vast trampoline with bowling balls scattered across it. Each bowling ball creates a dimple, and marbles rolled nearby curve toward the dimples, spiraling inward or orbiting around. It's a crude visualization. Real space-time is four-dimensional and doesn't literally stretch like rubber, but it captures something essential. Geometry matters. Shape matters. The fabric of existence is not flat. Your mattress pressing against your back is a tiny dimple in space-time. Earth is a bigger dimple beneath that. The sun, far away, creates an enormous well that curves space-time across millions of kilometers, and all of it is connected, all of it interacts, all of it obeys Einstein's field equations whether anyone is watching or not. The ceiling fan above you traces its circle through this curved space. Its motion is affected by Earth's gravity, which means it's affected by Earth's space-time curvature. The fan doesn't know this. Fans are not known for their geometric awareness, but every rotation is a journey through warped existence, a path determined by the distribution of mass in its neighborhood. Einstein's equations predicted phenomena no one had imagined: the bending of light around massive objects, the existence of black holes, regions where space-time curves so severely that nothing can escape, the expansion of the universe itself, space-time stretching in every direction, gravitational waves, ripples in the fabric of existence created by accelerating masses. All of this followed from one insight: gravity is not a force. Gravity is geometry, and the falling elevator, the floating astronaut, the accelerating rocket, they were the first hints that Isaac Newton's clockwork universe was only an approximation, a local simplification of a far stranger cosmic truth. The mattress holds you, space-time curves around you, and somewhere, in the equations Einstein wrote down over a century ago, your existence is already accounted for. A tiny perturbation in the fabric, a story written in the language of geometry. Imagine you're holding a bedsheet stretched tight between your hands, pulled taut like a drumhead. The fabric is smooth, flat, uniform. Now place a bowling ball in the center. The sheet sags, dimpling downward, creating a depression that curves the fabric around the ball's weight. This is the most common visualization of general relativity, and despite its flaws, real space-time is not two-dimensional, does not require something outside to curve into, and is not made of cotton. It captures something profoundly true. Mass creates curvature. Objects respond to that curvature. What we call gravity is just geometry in action. Roll a marble across your tilted bedsheet. If the sheet were flat, the marble would travel in a straight line. But with the bowling ball creating a dip, the marble curves toward the center, spiraling inward, or, if it's moving fast enough, orbiting around. The marble thinks it's going straight. There's no force pushing it sideways, but the geometry of the surface is guiding its path. Now multiply this by 2 dimensions. The bowling ball's dimple isn't just pulling the sheet downward, it's warping the sheet in every direction, creating a 3-dimensional influence zone that extends outward from the ball. Objects approaching from any angle will curve toward the center, following the geometry. Now add time. This is where the visualization breaks down, but stick with me. In general relativity, space-time is a 4-dimensional fabric, and mass doesn't just curve space, it curves time too. Near a massive object, time passes more slowly. Clocks tick at different rates depending on how deep they are in the gravitational well. This isn't a separate effect from the spatial curvature. It's part of the same geometric distortion. Space and time mixed together in a single warped fabric. Your feet, dangling closer to Earth's center than your head, are deeper in the gravitational well. They're experiencing more curvature, and as a result, they're aging more slowly than your head, Not by much, not by anything you'd notice, but by an amount that atomic clocks can measure with absurd precision. Historians still argue whether Einstein himself thought of space-time curvature in such geometric terms, or whether he viewed the mathematics more abstractly. His collaboration with the mathematician Marcel Grossmann was essential for developing the differential geometry needed for general relativity. Einstein reportedly told Grossmann that he needed help because the math was beyond him. But once the equations were established, the geometric interpretation became standard, a way of visualizing what the symbols meant. Here's a quirky detail that grounds this in reality. The global positioning system in your phone depends on gravitational time dilation. GPS satellites orbit at about 20,000 kilometers altitude, where gravity is weaker and time passes slightly faster than on Earth's surface. The difference is tiny, about 45 microseconds per day, but if uncorrected, it would cause positioning errors of several kilometers within hours. Engineers program the satellites to account for relativity, adjusting their clocks to match Earth-based time. Without Einstein, your map app would be useless. You let your eyes rest, picturing the invisible curvature around you. Earth's mass bends space-time, creating a well that extends outward in all directions. The Moon follows the contours of this well, tracing an orbit that appears elliptical from above but is actually a straight line through curved four-dimensional geometry. The Sun creates a larger well, and Earth orbits within it. The galaxy creates an even larger well, and the Sun drifts along its curves. It's wells within wells, curvature nested inside curvature, all the way up to the cosmic scale, where the distribution of all mass and energy in the universe shapes the overall geometry of existence. Cosmologists debate whether the universe is ultimately flat, curved like a sphere, or curved like a saddle. The answer depends on the total density of matter and energy, and current measurements suggest it's very close to flat, but not exactly, not quite, with subtle curvatures that we're still trying to measure. The bedsheet analogy fails in so many ways. It suggests there's something underneath space-time for it to curve into, but there isn't. Space-time is all there is. It suggests gravity requires a third dimension to create the dip, but real gravity is intrinsic curvature, like the surface of a sphere curving without reference to any external space. It suggests the bowling ball is resting on the fabric, but in reality, the mass is inside the fabric, part of it, inseparable from the geometry it creates. But for tonight, lying here, the bedsheet will do. Imagine your mattress as a tiny depression, your body as a gentle curve, your thoughts as paths through a warped landscape. The ceiling fan rotates in this landscape, following contours invisible to the eye but present in the equations. Everything curves, everything follows the geometry, everything obeys the rules Einstein wrote down a century ago. And in that curvature, time itself bends. Clocks run slower near mass. The future arrives at different rates depending on where you stand. Your feet and your head, separated by 2 meters, are separated by more than just space. They're separated by time too, in a way that Newton never imagined. Let's talk about time again. Specifically, let's talk about how gravity steals it. You're standing at sea level, on a beach somewhere warm, waves lapping at your feet. The sand shifts beneath your weight, and the sun hangs low on the horizon, painting everything golden. You're wearing a watch, a very good watch, the kind that loses only 1 second every million years, and it's ticking along, measuring time in its precise mechanical way. Now imagine your identical twin is standing at the top of a mountain. Not just any mountain, let's say Everest, about 9 kilometers above sea level. They're wearing an identical watch, synchronized with yours to the nanosecond before you parted ways. They're cold and breathless and regretting their life choices, but they're there, watching time pass. A week later, you reunite at base camp. You compare watches. They don't match. Your watch at sea level has ticked slightly fewer times than your twin's watch at altitude. The difference is absurdly small, maybe a few nanoseconds, but it's real, measurable, confirmed by countless experiments with atomic clocks. Time at sea level passes more slowly than time at altitude. Gravity, it seems, is dragging on time itself. This is gravitational time dilation, and it's one of the strangest predictions of general relativity. Near a massive object, space-time is more curved, and one consequence of that curvature is that time runs slower. The deeper you are in a gravitational well, the more time you lose compared to someone higher up. Your feet know this. They're slightly closer to Earth's centre than your head, slightly deeper in the well, experiencing slightly more gravitational time dilation. Over a lifetime, your feet age less than your head by something like 90 billionths of a second. It's not much, but it's not nothing. Historians still argue whether Einstein anticipated all the experimental confirmations of gravitational time dilation, or whether some surprised even him. The theory predicted it clearly, but testing required technologies that didn't exist in 1915. It wasn't until 1959, when Robert Pound and Glenn Rebka measured the frequency shift of gamma rays travelling vertically in a tower at Harvard, that gravitational time dilation was directly confirmed on Earth. The experiment was delicate, precise, and exactly matched Einstein's predictions. Here's a quirky detail that connects this to your daily life. The clocks on GPS satellites run faster than clocks on the ground, because they're higher up and experiencing less gravitational time dilation. At the same time, they're moving fast enough that special relativistic time dilation, velocity-based, not gravity-based, slows them down. The two effects partially cancel, but not completely. The net result is that satellite clocks gain about 38 microseconds per day compared to ground clocks. Engineers correct for this continuously, keeping your map accurate. You breathe slowly, feeling the pull of gravity as weight against your back. That pull is also a pull on time. The closer you are to massive objects, the slower your clock runs relative to distant observers. If you could hover near a neutron star where gravity is billions of times stronger than Earth's, time would crawl compared to someone far away. Near a black hole's event horizon, time would nearly stop. External observers would see you frozen in place, aging imperceptibly, suspended on the edge of infinite curvature. But you're not near a black hole. You're in bed, in a normal gravitational field, on a planet that's gently curving space-time without doing anything dramatic. Time is passing for you at almost exactly 1 second per second, with only the tiniest corrections for altitude and motion. The ceiling fan above you traces its circle through this curved time. Each rotation takes a certain duration, and that duration depends, imperceptibly, but truly, on the fan's distance from Earth's centre. If you move the fan higher, it would tick faster. Lower, slower. The geometry demands it. Now let your breathing deepen. Let your muscles release. The journey we've taken tonight has covered centuries of physics, from Newton's clockwork to Einstein's curved space-time, from Swiss patent offices to GPS satellites orbiting far above. You've travelled through time dilation and length contraction, through simultaneity's relativity and mass energy equivalence, through falling elevators and stretched bed sheets. And now it's time to rest. The universe will keep curving while you sleep. Stars will bend light around themselves. Planets will trace geodesics through warped space. Clocks at different altitudes will tick at different rates, too slowly for anyone to notice but real all the same. Your body sinks deeper into the mattress, and the space-time around you holds its shape, gentle and constant. The ceiling fan turns, a metronome marking seconds that are neither absolute nor universal but yours, specifically yours, in this moment, in this place. Tomorrow you can think about black holes. Tomorrow you can wonder about wormholes and time paradoxes, and the ultimate nature of temporal existence. But tonight, let the curvature cradle you. Let gravity hold you down in the kindest sense. Let time pass at whatever rate it chooses, carrying you gently forward. Close your eyes if they're not already closed. Feel your breath. Feel the weight. Feel the seconds stretching out like taffy, slow and sweet and soft. You're safe here in this little dip in space-time. The equations balance, the geometry holds, and time, strange, flexible, endlessly surprising time, flows around you like water around a stone, carrying you toward morning with patient, unhurried grace. Rest now, you've earned it. Morning will bring new questions, of course, it always does. But for now, in this quiet space between waking and sleeping, there's one more practical truth worth knowing. The physics you've been drifting through isn't just theoretical, it's embedded in your pocket. Your phone knows where you are, not approximately, not within a city block, but precisely, within a few meters, sometimes better. It accomplishes this miracle through a constellation of satellites, each one broadcasting a time signal, each one allowing your phone to triangulate its position based on the tiny differences in when those signals arrive. This is the global positioning system, and it would be completely worthless without Einstein. The satellites orbit about 20,000 kilometers above Earth, moving at roughly 14,000 kilometers per hour. From their perspective, time passes differently than it does on the ground. Two effects compete. Their altitude means weaker gravity, so gravitational time dilation speeds their clocks up. Their velocity means special relativistic time dilation slows their clocks down. The net effect is that satellite clocks gain about 38 microseconds per day compared to identical clocks at sea level. 38 microseconds sounds trivial, but light travels about 11 kilometers in 38 microseconds. If the satellite clocks weren't corrected for relativity, your phone's position calculations would drift by kilometers within hours. By the end of a day, the GPS system would be useless. Your map would show you standing in the wrong neighborhood, the wrong city, possibly the wrong continent. Engineers anticipated this. The satellite's atomic clocks are deliberately set to run slow before launch, so that once they're in orbit and experiencing the combined relativistic effects, they'll tick at the same rate as ground clocks. It's a beautiful example of theoretical physics becoming practical engineering. Einstein's century-old equations programmed into military hardware and consumer electronics alike. Historians still argue whether the GPS system's designers fully appreciated the relativistic corrections, or whether they were added as an afterthought. Some accounts suggest early engineers were skeptical that relativity mattered at such slow orbital speeds. Others indicate that relativistic effects were included from the beginning. Either way, modern GPS is a working proof of general relativity, broadcasting confirmation of Einstein's theory thousands of times per second. Here's a quirky detail that might amuse you. The first GPS satellites were launched by the US military in the 1970s during the Cold War, primarily for tracking submarines and guiding missiles. The civilian applications, navigation apps, fitness trackers, Pokemon Go came later. Every time you use your phone to find a coffee shop, you're benefiting from both nuclear anxiety and curved space-time. You might wonder whether you could detect relativistic effects without satellites. The answer is yes, but it requires sensitive equipment. In 2010, researchers at the National Institute of Standards and Technology demonstrated gravitational time dilation by comparing two atomic clocks separated by only 33 centimeters of height. The higher clock ran faster, as relativity predicted. The difference was about 1 part in 10 to the 17th, impossibly small, yet real and measurable. This precision opens strange possibilities. With sensitive enough clocks, you could map gravitational fields by tracking time differences. You could detect underground structures by measuring how they affect local time flow. You could, theoretically, build a gravitational clock that tells you not what time it is, but how curved space-time is in your location. Geologists and prospectors would love such devices. They'd reveal hidden oil deposits or mineral veins through time itself. The ceiling fan above you cares nothing for GPS or atomic clocks. It operates in the Newtonian regime, where time is absolute enough for all practical purposes. But the physics that governs that fan is the same physics that governs your phone's satellite connection. It's all one continuous reality, from the spinning blades above your head to the orbiting satellites 20,000 kilometers up. And somewhere in that continuity, time keeps flowing, at different rates, in different places, for different observers, but always forward, always toward whatever comes next. Your phone sits on the nightstand, its GPS chip dormant but ready. Tomorrow it will help you navigate, using signals that have been adjusted for relativity, carrying information shaped by the curvature of space-time. Tonight it just glows faintly in the dark, a tiny window into a universe that runs on Einstein's rules whether you're paying attention or not. The satellites drift overhead in their orbits, falling perpetually around Earth, their clocks ticking slightly fast but corrected to match yours. They don't know they're proving relativity. They don't know anything. But the math works, the signals align, and your map shows the right blue dot. Physics isn't just about abstract truths. Sometimes it's about finding your way home. Now let your thoughts drift outward, past the satellites, past the moon, past the planets, out to where space curves most dramatically, out to where time itself becomes trapped. Black holes are the universe's ultimate gravitational wells. They form when massive stars die, collapsing under their own weight until all their mass is concentrated in a single point, a singularity, surrounded by a boundary called the event horizon. Cross that boundary and there's no return. Not because you're pulled back by some extraordinary force, but because space itself curves inward so severely that every possible path leads toward the center. Imagine approaching a black hole. You're in a spacecraft descending slowly, watching the starfield shift around you as the hole's gravity bends incoming light. At first, you notice subtle changes. Time on your ship starts lagging behind time for your colleagues waiting safely at a distance. Your clock, watched through a telescope back home, appears to tick slower and slower. Your movements seem languid, almost frozen, as if you're trapped in thickening honey. From your perspective, nothing feels different. Your clock ticks normally. Your heart beats at its usual rate. You experience no slowing, no stretching, no strange pressure, at least not yet. But relative to the outside universe, you're crawling toward the horizon at an ever-decreasing pace. As you approach the event horizon, the effect becomes extreme. Outside observers see you slow down asymptotically, never quite reaching the boundary. Your image reddens as photons stretch their wavelengths climbing out of the gravitational well. Eventually you fade from view, your last moment frozen in light that takes longer and longer to escape, until you simply vanish into darkness. But from your perspective, you cross the horizon without fanfare. There's no wall, no barrier, no sign that says point of no return. You simply pass through, and the universe outside becomes unreachable. Light from the outside can still fall in, so you might see the stars for a while, but no signal you send will ever climb out. You're beyond the edge of communication, falling toward the singularity where known physics breaks down. Historians still argue whether black holes were an intended prediction of general relativity or an unwanted consequence. Einstein himself was skeptical that such objects could exist. He published a paper in 1939 arguing that nature would prevent the formation of singularities. The term black hole wasn't coined until 1967 by the physicist John Wheeler, decades after the theoretical groundwork was laid. Here's a quirky detail that might spark wonder. Time doesn't just slow near black holes. At the event horizon of a non-rotating black hole, time theoretically stops relative to distant observers. A clock at the horizon would appear frozen forever, its hands never moving, its seconds stretching into eternity. Of course, no clock could survive at the horizon. Tidal forces would tear it apart. But the mathematical prediction holds: infinite time dilation at the boundary of no return. What happens inside the horizon is murkier. General relativity predicts that everything falls toward the singularity, a point of infinite density and zero volume where space-time curvature becomes infinite. But physicists suspect that quantum effects, ignored by general relativity, must become important near the singularity, preventing true infinity and replacing it with something else. We don't know what that something is. Our theories break down where we need them most. The ceiling fan above you has nothing to fear from black holes. The nearest one to Earth, that we know of, is over 1,000 light-years away, far enough that its gravitational influence is utterly negligible. You live in a gentle neighbourhood of space-time, far from the cosmic extremes where time stops and space folds in on itself. But those extremes exist. The universe contains millions, perhaps billions of black holes, remnants of dead stars lurking at the centres of galaxies, slowly consuming matter that drifts too close. Each one is a region where time behaves strangely, where gravity reaches infinite strength, where the rules you've learned tonight reach their breaking point. You're drifting now, imagining the darkness of a black hole's interior. No light escapes, so there's nothing to see, only falling toward a fate unknown. Time passes, but how much? The equations can't say. The singularity waits, patient and inevitable. But you're not there. You're here, in bed, in a friendly gravitational field that curves space-time just enough to hold you down without hurting you. The darkness behind your closed eyelids is comforting, not cosmic. The seconds tick by at their normal rate, give or take a few nanoseconds you'll never miss. Black holes are out there, time traps and light prisons scattered through the galaxy. But they're not your concern tonight. Tonight you rest, safe from singularities, cradled in the gentle curvature of home. If black holes are time's trapdoor, then wormholes might be its secret passage. The idea is simple, at least conceptually. Take 2 points in space-time, say, here and a galaxy far away, or now and a century ago, and connect them with a shortcut. A tunnel through the fabric of existence, bypassing the normal distance or duration between locations. Step through one end, emerge from the other, having crossed space or time in ways that ordinary travel forbids. The physics is more complicated. General relativity allows for such structures, mathematically speaking. The equations don't prohibit wormholes. They describe them as possible solutions, configurations of curved space-time that connect distant regions. But allowing something mathematically isn't the same as ensuring it exists physically. The universe might contain wormholes, or it might not. We've never seen one. Einstein himself explored these solutions in 1935, collaborating with Nathan Rosen to describe what they called bridges in space-time. Later physicists realized that these Einstein-Rosen bridges, if they existed, would be unstable. They'd collapse faster than anything could traverse them. To keep a wormhole open long enough to be useful, you'd need exotic matter with negative energy density, and it's not clear whether such matter exists or can be created. But let's imagine, for a sleepy thought experiment, that you found a stable wormhole. Its mouths, two spherical regions in space, are connected through a tunnel that bends through a higher dimension. You approach one mouth, pass through, and emerge from the other, having travelled across the universe in moments. The relativistic implications are dizzying. If one mouth of the wormhole is accelerated to near light speed and then brought back, it experiences time dilation relative to the other mouth. The clocks at the two ends desynchronize. Pass through the wormhole and you might emerge not just in a different place but in a different time. The past potentially relative to where you started. This is where physics flirts with science fiction. Time travel, not through some magical device, but through manipulated geometry. Move wormhole mouths around, age them differently, and the tunnel between them becomes a bridge through time. Historians still argue whether Einstein took wormholes seriously or considered them mathematical curiosities. His 1935 paper was primarily concerned with quantum mechanics and the relationship between black holes and elementary particles, not with practical traversal. The time travel implications were explored by later physicists, including Kip Thorne, who in the 1980s investigated whether wormholes could theoretically be used for backward time travel. Here's a quirky detail that might entertain you. Carl Sagan, while writing his novel Contact, asked Thorne whether there was a scientifically plausible way for his characters to travel vast distances quickly. Thorne suggested wormholes, and his exploration of their physics led to several serious research papers. A science fiction novel prompted legitimate theoretical work. Sometimes imagination and science dance together. The catch, there's always a catch, is that backward time travel creates paradoxes. If you travel to the past, you might prevent the events that led to your time travel, creating logical contradictions. You might meet your younger self, warn them about dangers, and change the future in ways that make your warning unnecessary. The universe doesn't like contradictions. Something must give. Physicists have proposed various resolutions. Perhaps the universe prevents paradoxes automatically, arranging events so that any time traveler's actions are already part of history. Perhaps traveling to the past creates a new timeline, branching off from the original. Perhaps the physics itself forbids backward time travel, imposing some unknown constraint that closes off wormholes before they can be used paradoxically. We don't know. The math allows wormholes. The universe might not. We've never detected one, never created one, never proven they're impossible. They remain theoretical possibilities, tantalizing shortcuts through space-time that might exist somewhere, somehow, or might be forever out of reach. The ceiling fan above you operates in a straightforward space-time, no shortcuts required. Its blades travel in circles, not through tunnels. It ages at the same rate as everything around it, give or take the tiny relativistic corrections you've learned about. No wormholes connect your bedroom to distant galaxies. No time travel awaits in your closet. But imagine, just for a moment, that somewhere in the universe, a stable wormhole exists. Its mouths shimmer in the void, connected by a tunnel that bends through dimensions you can't visualize. Civilizations might use it for trade, for exploration, for communication across distances too vast for light to bridge in reasonable time. Or it might float alone, undiscovered, a secret passage waiting for someone curious enough to find it. You'll never see it. But it's nice to imagine it's there. Every discussion of time travel eventually runs into the grandfather paradox. It's almost obligatory, like mentioning Schrödinger's cat in quantum mechanics, or the butterfly effect in chaos theory. But the grandfather paradox isn't just a cliché. It's a genuine puzzle that physicists take seriously, even if they can't solve it. The setup is simple. You build a time machine, or find a wormhole, or discover some other method of travelling backward, and you use it to visit your own past. Specifically, you visit the time before your parents were born and you prevent your grandfather from meeting your grandmother. Without that meeting, your parent is never born. Without your parent, you are never born. And without being born, you can't travel back in time to prevent the meeting in the first place. Contradiction. Logical impossibility. The universe seems to prohibit your actions, yet you performed them. What gives? One resolution is simple. Backward time travel is impossible. The laws of physics somehow prevent it. Perhaps wormholes can't be stabilized. Perhaps any attempt to create a time machine causes it to collapse or explode or simply fail. The universe protects itself from paradoxes by forbidding the tool that would create them. But this feels unsatisfying. General relativity allows solutions that look like time travel. The math works. Why would physics permit the equations but forbid the reality? Another resolution invokes self-consistency. Perhaps any time traveller who visits the past is already part of history. You can't change what happened because what happened already includes your visit. You might try to prevent your grandfather from meeting your grandmother, but you'll fail. Something will go wrong, some coincidence will intervene, and the meeting will happen anyway. The universe arranges itself so that paradoxes never arise. Historians still argue whether this self-consistency principle is a law of physics, a likely feature of any time travel scenario, or wishful thinking. The physicist Igor Novikov proposed it as a serious constraint, arguing that only self-consistent histories are physically possible. If true, time travelers have no free will in the past. They can only do what was always done. Here's a quirky detail that might help you sleep. Some physicists suggest the paradox dissolves if time travel creates branching timelines. You travel to the past and prevent your grandparents meeting, but in doing so, you create a new timeline where you were never born. The original timeline, where you were born and built the time machine, still exists, untouched. You can't return to it, but it hasn't been erased. Paradox avoided through multiplication. This many worlds approach borrows from quantum mechanics, where particles exist in superpositions and measurements, split reality into parallel branches. But applying it to time travel is speculative at best. We have no evidence that timelines can branch, no method for testing the hypothesis, no way to know if the resolution is real or just comforting fiction. The grandfather paradox has siblings. The bootstrap paradox asks, what if you travel back in time and give your younger self the plans for the time machine? Where did the plans originate? They exist in a loop, caused by themselves, with no external origin. Information appears from nowhere, circling endlessly through time. Or consider the information paradox. If you travel back and tell people about future technology, you accelerate progress, which changes the future, which changes what you know. Causality becomes tangled, effects preceding causes, the universe twisting itself into knots. These paradoxes haunt physicists' dreams, not because time travel is imminent, but because they probe the deepest questions about causality, consistency, and the nature of time itself. If the universe forbids backward time travel, why? What mechanism enforces the prohibition? And if it allows time travel, how does it handle the contradictions? You lie still, feeling your heartbeat, feeling time flow forward as it always has, one moment giving way to the next. No paradoxes here, no loops, just the familiar arrow pointing from past to future, carrying you along. The ceiling fan rotates, and each rotation follows the previous one, leading to effect in an unbroken chain. You breathe, and the breath that fills your lungs is different from the breath you expelled. Time has passed, change has occurred, the universe has moved forward. This is normal, this is safe, this is the way things have always worked. But somewhere in the equations, in the abstract possibilities that physics allows, time might flow differently. Loops might form, paradoxes might threaten, and the universe might have subtle ways of protecting itself, ways we don't yet understand. Tonight you don't need to understand them. Tonight you rest in linear time moving forward, letting tomorrow arrive the old-fashioned way, 1 second at a time. Why does time move forward at all? It's a question so basic that most people never think to ask it. Of course, time moves forward. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat. Memories form of the past but not the future. The direction of time is as obvious as up and down. But the laws of physics don't see it that way. Almost all fundamental equations work equally well whether time runs forward or backward. If you recorded a collision between two particles and played the recording in reverse, the reversed version would obey the same laws as the original. Particles don't care which direction time flows. Their interactions are symmetric. So where does the asymmetry come from? Why do we experience a clear arrow of time pointing from past to future when the microscopic rules allow both directions equally? The answer, most physicists believe, lies in entropy. Entropy is a measure of disorder, of how many different ways the parts of a system can be arranged. A neat stack of papers has low entropy. There's only one way to arrange them in that specific order. A scattered mess on the floor has high entropy. Countless arrangements would look equally messy. The second law of thermodynamics says that entropy tends to increase. Systems move from order to disorder, from special configurations to typical ones. Heat flows from hot to cold, ice melts in warm rooms, eggs scramble but don't unscramble. This is why time has a direction. The past was lower in entropy, the future is higher. We remember the past because memory formation increases entropy. Writing information to your brain requires energy expenditure and heat dissipation. We can affect the future but not the past because our actions inject entropy into the universe, pushing it further along the arrow. Historians still argue whether entropy alone explains the arrow of time, or whether additional principles are required. Some physicists point out that the second law requires a low entropy starting condition. The Big Bang must have been extremely ordered for entropy to have been increasing ever since. Why was the beginning so special? The law doesn't say, it just assumes. Here's a quirky detail that might keep one neuron firing. In a vast enough universe, given enough time, random fluctuations might occasionally decrease entropy locally. Scattered molecules might spontaneously reassemble into an ordered state. This is overwhelmingly unlikely, vastly more unlikely than anything you can imagine, but not forbidden by the laws of physics. If you waited long enough, an egg might unscramble itself purely by chance. The physicist Ludwig Boltzmann, who developed much of the mathematics of entropy in the 19th century, was troubled by these questions. He proposed that our observable universe might be a random fluctuation in a larger, infinitely old cosmos, a brief dip in entropy surrounded by eternal disorder. The idea has problems, but it shows how deeply physicists have grappled with the arrow of time. You feel yourself drifting, and the arrow carries you along, past giving way to future, wakefulness giving way to sleep, order giving way to the gentle disorder of rest. The ceiling fan above you is a small entropy machine. Electrical energy enters, mechanical motion results, heat dissipates into the air. The total entropy of the universe increases with every rotation. The fan can't run backward spontaneously, reassembling the dissipated heat into electricity that would decrease entropy, violating the second law. Time flows forward for the fan just as it flows forward for you. But why? Why did the universe begin with low entropy? Why is there an arrow at all? These questions remain open, debated, uncertain. Physics describes the arrow. It doesn't fully explain it. Something about the initial conditions of existence set up the asymmetry, and we've been riding it ever since. Tonight you ride it toward morning. Your metabolism burns fuel, increasing entropy. Your dreams shuffle memories, reorganizing information, dissipating order into the warm darkness of sleep. The arrow doesn't pause or reverse, it carries you steadily forward, one moment at a time. And somewhere in the equations the mystery remains. Time flows forward because entropy increases. Entropy increases because time flows forward. The logic circles touching something deep, something we don't quite understand. But you don't need to understand it to ride it. You've been riding it your whole life, and you'll keep riding it until the arrow stops pointing anywhere at all. After everything, Newton's clockwork, Einstein's space-time, entropy's arrow, you might expect physicists to agree on what time actually is. They don't. The debates are ancient and ongoing. Is time a fundamental feature of reality, built into the universe from the start? Or is it emergent, arising from deeper structures like temperature arises from molecular motion? Does the past still exist, frozen in the block universe of space-time, or does only the present moment have genuine being? These questions have no consensus answers, even after centuries of philosophy and a century of relativity. Some physicists embrace the block universe interpretation. In this view, space-time is a four-dimensional block containing all events, past, present, and future, coexisting eternally. Your birth is in the block. Your death is in the block. Every moment of your life is frozen there, as real as any other. The flow of time is an illusion, a feature of conscious experience rather than physical reality. Others reject this view as incomplete or misleading. They argue that the present moment has a special status, that change is real, that the future doesn't exist yet in any meaningful sense. The block universe, they say, can't capture the dynamism of existence, the feeling that time is genuinely passing rather than merely being traversed. Historians still argue whether Einstein himself believed in the block universe. In a famous letter of condolence after the death of his friend Michel Besso, Einstein wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. This suggests he took the block view seriously, but other quotes are more ambiguous, and Einstein was never a systematic philosopher. Here's a quirky detail that might linger in your thoughts. Some interpretations of quantum mechanics suggest the future isn't fixed until observed. If so, the block universe might not be a block at all, more like a tree, with branching possibilities collapsing into definite outcomes as time passes. The future would be genuinely open, not yet written into space-time, waiting to be determined. But quantum mechanics and general relativity don't play well together. They describe different domains, the very small and the very massive, and attempts to unify them into a single theory have stalled for decades. Quantum gravity, if we ever achieve it, might reveal whether time is fundamental or emergent, whether the block universe is real or a mathematical artifact. Some researchers have proposed that time emerges from entanglement, the quantum connection between particles. Others suggest it arises from increasing complexity, or from the relationships between systems, or from something we haven't thought of yet. The field is scattered with speculations, none of them proven, all of them fascinating. You might find this uncertainty disturbing or liberating. After all this science, after all these equations and experiments, we still don't know what time is. We know how it behaves, dilating, curving, flowing in one direction, but not what it is at the deepest level. The mystery remains. The ceiling fan above you keeps rotating, indifferent to metaphysics. Its behavior is predictable, its physics well understood, its connection to fundamental questions about time nearly non-existent at this scale. It spins because you turned it on. It will stop when you turn it off. Simple causality, simple mechanism, simple life. But somewhere beneath that simplicity the questions persist. Why does now feel special? Why can't we remember tomorrow? Is the you lying here the same you who woke up this morning, or a different pattern of matter claiming continuity? Time braids through these puzzles, connecting physics to philosophy to the experience of being conscious in a universe that doesn't explain itself. You let the questions drift. You don't need answers tonight. The fan spins, time passes, morning approaches, carried by whatever mechanism time actually is, and in the not knowing, there's a kind of peace. The universe is stranger than you thought, stranger than anyone fully understands. You're part of that strangeness, embedded in space-time, riding the arrow, experiencing the mystery from inside. Tomorrow you can read more, think more, argue about interpretations with anyone patient enough to listen. But tonight, the mystery holds you gently, and that's enough. You're back where you started. The same bed, the same ceiling fan tracing its slow circles through the air. The same body heavy with approaching sleep, breathing in the same rhythm that's carried you through every night of your life. But something has changed. You know, now that time is not what you thought. Not a river flowing uniformly for everyone, not a cosmic metronome counting identical seconds throughout the universe. Time is personal. Time is geometric. Time is shaped by motion and mass, curved by gravity, stretched by velocity, experienced differently by different observers in ways that are not metaphorical but physical, measurable, real. Your feet are aging slightly slower than your head. The GPS satellites overhead are ticking slightly faster, corrected by engineers who take Einstein seriously, because the universe does. Somewhere, far away, black holes trap time itself, freezing anything that crosses their horizons into eternal stillness from the outside view. And the arrow of time points forward because entropy increases, because the past was special, because something about the beginning of everything set up an asymmetry that we've been riding ever since. You're a time traveller, you always have been. Not the dramatic kind from movies jumping decades in a flash, but the steady kind, moving through the fourth dimension at the rate of 1 second per second, give or take a few nanoseconds you'll never miss. The ceiling fan doesn't know any of this. It just spins, following the same physics it's always followed, the same physics everything follows. Newton's approximation works fine for ceiling fans, but underneath that approximation, Einstein's truth holds. Space and time are woven together, curved by presence, experienced relatively. Historians still argue about many things, but they don't argue about whether relativity is real. The experiments have been run, the predictions have been confirmed. Your phone works because relativity works. Your understanding of the universe, however sleepy, is grounded in a century of testing. Here's one last quirky detail to carry into sleep. Every second that passes for you, photons are crisscrossing the universe at light speed, experiencing no time at all. Light left distant stars millions of years ago by our reckoning. But from the photons' perspective, they departed and arrived instantaneously. The universe, for light, is a single moment stretched across all of space. You're watching that moment whenever you see anything. Images carried by travellers who don't age, don't wait, don't experience duration. And you, lying here, are experiencing duration. Seconds stretching into minutes, wakefulness fading into dreams, the present sliding into the past, making room for a future that doesn't exist yet, or does exist depending on which interpretation you prefer. It doesn't matter which you prefer. The equations are the same either way. The physics doesn't care about your metaphysics. Time will pass or already has passed, or is passing eternally in a frozen block that only feels like flowing. You'll experience it as you always have, moment by moment, breath by breath, heartbeat by heartbeat. The ceiling fan completes another rotation. You don't count them anymore. They become background, soothing in their predictability. Outside your window, the Earth rotates too, a larger circle marking larger time, days, not seconds, while orbiting the Sun, marking years, while the Sun orbits the galaxy, marking hundreds of millions of years you'll never notice. Circles within circles, times within times, and you, at the centre of your own experience, feeling it all from inside. You've travelled far tonight, from Newton to Einstein, from patent offices to black holes, from GPS satellites to the beginning of the universe, and you've arrived back here, in bed, exactly where you started, having moved through time in the ordinary way while learning about its extraordinary nature. Tomorrow you might think about this again, or you might forget, letting the knowledge settle into the background like the fan's hum. Either way, time will keep doing what time does, passing, curving, flowing forward, carrying you along. Close your eyes, let the fan spin, let the seconds stretch like taffy, soft and slow and sweet. You're exactly where you're supposed to be, in space-time, in this moment, in this gentle curve of existence that holds you and everything you've ever known. Rest now. The universe will keep turning while you sleep, and when you wake, time will still be there, strange and familiar, personal and cosmic, yours to experience one moment at a time. Sweet dreams, traveller, you've earned them.